if you catch the value of the output, maybe they have something the logical wrong or logical error in your program. So we should care about the logic. So it is the basic or it is the right way. That means we prefer to think over about our question. That means when we translate our the real question or real sentence into just the program code, we first translate into logical expression. And based on the logical expression, then we can let the computer do their computation. But in computer computation, it's just do their inference. So this inference we have already to show that if you let the computer to do some inference, for example, you give this just a condition, and from this condition you just want to get the final result Q. That means whether or not from P we can inference Q, we just write like this: from P can imply Q. And what's the computer to do that? Computer just translate this the inference or this proof into just the P condition Q. This is a tautology. That means it is always true. If this expression, logical expression, P condition Q, maybe this P can be also, for example, it may be A, B, C, for example. That means this P maybe it can be also is a logical expression. We don't care about this. And also maybe the final result is also is the logical expression. For example, C, B, R, or A. For example, it also is a logical expression. No matter, okay. That means from the condition to this result, we just using the condition logic symbol and combine together. And they combine to just the new logic expression. If we just make or check it is always true, then we can say it is okay. So computer to do their proof or to do their inference, just to translate this to the logic or other new logic expression. This new logic expression and check this logic expression whether or not it is tautology. Always true. And we, in the previous session or previous videos, we just show about this. And now we just extend this inference. We just inference, just do the inference with the quantifying statement. That means we just to this proof or this inference just care about the quantify symbol. That means we have two quantify symbols. The first is for all, also for all, and then is for some, okay? And we also have these the four, just the inference rules. The first is for all, we just call it universal. It is universal for all, and this is the extension. And just for this, we have the instantiation. Is the instantiation, and secondly is the generalization. What's their difference? Instantiation, here is one instantiation, and the two is the generalization. Instantiation means that it is a special. That means from this we can know that it is over bar is maybe condition, and here over the under the bar we know that is the result. That means if we know that for all x px, here px add x have the just the feature of p, then we can say for the special element c, this c is one special or particular member of the domain, then we can say, although we know that for all x, we x satisfy p, then we can say for the special member c, of course, they are also satisfying p, so we can say for all x px, for all x px, so your symbol means so p pc is okay. And the second generalization means that we, from the word meaning is generalization. That means you have many the evidence, and from the evidence you can just summarize something the new theory or new rules or new answer. So the similarly here is a condition that means now we know that we already check for all the arbitrary C that satisfies the P. So we just get the rule or get the result. That means so for all x px, for example, if your monitor to check all of your students or members have already to do already done for your homework one, then we can get the result that for all your students in your class that have already done for the homework one. So it is called the generalization. So instant or generalized. So from this word you can choose understand what you mean. Instant means that from all the general rules to influence some the special things. And general things mean that we just for many the special things to summarize and just the general rules. Okay, and just for the just for some or for extension qualified it has the same. That means it is the instance and generalized. Okay, instance means that if we say for some x px, so we can say for some element. If we tell it is for some element, not for any or arbitrary. Okay, and similarly, if we know that then for some special element C we have PC, then we can say for some x px. So just we have this for the special rules for this logic statement with the qualified symbol. Okay. Here is a special example, and we have many examples in the later the video. Now we are just pause for this. Okay, now give you just the special video to continue to learn about this inference rule with the qualifiers. Okay. About how to use the rules of inference to make a valid argument, and we're going to continue doing that. And in this video, we're going to focus on statements that have quantifiers. What we would like to do is to develop some rules that we can use when we're dealing with quantified statements. And our first rule here is universal instantiation, which we just abbreviate the TI. And essentially what it says is if we have a statement that says for all of a domain, some fact is true, such as, let's say, you're telling us that all dogs are cute. So that's for all dogs, basically they are cute. And then I tell you, and that's of course for the universe of all dogs. Then I tell you, Oliver is my dog. Or a dog, either one. This rule essentially allows me to get rid of that quantifier of for all and instead talk specifically about one element in the domain. My dog Oliver is an element in the domain, and therefore I can say that P-O, we just use O for Oliver, which essentially means Oliver is cute. The universal generalization is essentially this rule backwards. So if I tell you that P of C is true for an arbitrary C, then essentially I'm saying it is true for all values. Now the important thing to remember with this rule is that we're talking about an arbitrary C, or essentially we're saying if we pick any old value that, from the domain, so some C value that belongs to our universe, then if it's true,
no matter which value we choose, essentially we're saying it's true for all values in the domain. Our next two rules should flow very easily from our last example, and that is existential instantiation and existential generalization. So again, on my first one is saying there exists some x such that p of x. So we're saying there is some value that makes this true. Therefore, I can say that it's true for some specific value. And that's really just the definition of existential. Same thing for existential generalization. It's just this backwards. So we're saying if P of C is true for some element of C, then we can say there exists some element X such that P of X is true. And of course, our very, very favorite, one that we use so very often, modus ponens. This is universal modus ponens. So for all x, if we know that P of x implies Q of x, then, and we know that P of A is true, therefore we know Q of A is true. So again, we've got that if-then statement, and whenever we have that if-then statement, when we can show that the first part is true, then we can show that the second part is true. Let's see if we can't work together to construct it. Then we can show.
So for this universal model components, these rules is also can be easy to implement for the previous rules because we know that for all x, if px then qx, px condition qx, then we just using ui universal instantiation. Then we have for the special a we have if pa then qa. That means p here we have pa condition qa, and now combined together with pa we have the qa. We have already to show about this other columns that was in the previous sessions. So combined together, just using the UI and MP, we just have this new UMP, just like this. Okay.
See if we can't work together to construct a valid argument to show if we know the premises every dog has four legs and Oliver is a dog, we can conclude that Oliver has four legs. So the first thing we want to do is come up with some predicate statements to help us to construct our argument. So I know here that I'm dealing with a dog and four legs. So I'm just going to let d of x denote that x is a dog. And I'm going to let f of x denote
The first one is just to translate.
So now that I have my predicates, I want to be able to write my premises using those predicates. So every dog has four legs, can be written, and again, this is saying every dog, so that's for all x that belongs to the domain. We're saying if it is a dog, then it has four legs. My other premise says Oliver is a dog. And so I'm going to say D, O, O for Oliver. So X is a dog, I'm saying DO, which means O is a dog or Oliver is a dog. So these are my two premises, and now I'm going to construct my argument. So let's see how we do. Number one, I'm going to use for all x, if d of x, then f of x. And that is a premise that was given to me. Now, what we just learned is that if that is true, then I can say, if it is true for all of x, then I can say it is true for a specific x. So if Oliver is a dog, then Oliver has 4 legs. And what's the reasoning? Universal instantiation from 1. Now I can use DO, which of course was another premise, that Oliver is a dog, so now I've used both of my premises. And because of that, I can conclude FO, which of course is that Oliver has 4 legs, and that's modus ponens using 2 and 3. Here's another question for us to try. This one is a little bit more complicated. If you want a challenge, go ahead and press pause right here and try this question first. If you just want me to go through it with you, then that is what we're going to do right now. So we are going to use the rules of inference to construct a valid argument showing that the conclusion someone who passed discrete math has not read the book follows from a student in discrete math hasn't read the book and everyone in discrete math passed the class. So the first thing I want to do, as always, is to come up with which predicates I will use. And in this case, I'm going to let d of x denote x is a student in discrete math. Then I'm going to let b of x denote that x read the book. And lastly, I'm going to let p of x denote that x passed the class. So those are all of the things that I know is something about reading the book, passing the class, and obviously that the person is in discrete math. So let's see if we can take some of these statements and write them using predicate like. So we'll get to this one here at the end. Let's start with a student in discrete math hasn't read the book. So we're saying a student, which means there exists a student, such that now we're saying it's a student in discrete math and they have not read the book. So a student in discrete math would be d of x, and they're in the class and haven't read the book. So remember, if it's a negation here, then I have to use that negation here. So not the x. So that's that first statement.
So here we just remember we have already tell you the general rules. Mean that if you just to translate these things such as this sentence into the logical expression with the existing qualified symbol, we should be careful for this and together with and. And just the previous example, we just for all, we just use the condition. For some, we combine together with and.
Now let's take a look at everyone in discrete math passed the class. So everyone tells us that for all students who are in the class, so that would be for all x, what do we know? The student is in the class and passed the class. So if the student, oops, not student x, sorry, not class, but discrete. So if that student is in discrete math, then that student passed the class.
So this next, this just these the two uh, sentence, just using the different the qualifier and there's a different qualified rule. We have already heard that if we just in extension, it's the for some x we just using and for all x we just using the condition logical symbol. It means for all everyone, everyone. So we just say if px then px. So if we just change the rule, that means we just say using the and as a previous format, then you should have a different meaning. You can just try to think it over by yourself about the meaning and have difference. That means for all x, dx and px different meaning for x, dx condition px.
X, dx implies dx. And what I'm trying to get to is right here. Someone who passed discrete math has not read the book. So what is my conclusion going to be? I want to prove that there exists some student X such that they passed the class and they did not read the book. Now, I haven't proved anything yet, but what I've done so far is I have organized my thinking so that I know what my premises are and what I want my conclusion to be. So now I'm going to move on to actually doing this work. Okay, so now we know what we know for where we're headed, and what we know is, of course, our premises, and where we're headed is our here and our conclusion. Now I want to figure out a valid argument using my rules of inference that helps me to use those two premises to arrive at the conclusion. Now, before I start all willy-nilly into what I prove, I know that this is where I want to end up. I want to end up at the conclusion. Well, how can I possibly end up at a conclusion that says there exist these things unless I can show that P of x is true for some x because there exists an x, and that not B of x is true for that x. So let's see how we get there. We're going to start just by using our first premise that there exists an x such that d of x and not b of x. And if it helps you to think about what d of x means, that they're in the discrete math class, and not b of x means either, not, they have not read the book. But I think that actually makes it a little bit more confusing. And the reason for me being able to say that is a premise. So that's where we are so far. Again, keep in mind where we're heading. And so what I don't like about that first premise is that there's a quantifier. Quantifiers are difficult to deal with, so that's why we have those new rules. And one of those new rules says that if it's true for some element in the domain, then I can say it's true for a specific element in the domain. There exists some element A such that D of A and not B of A. And that's EI, existential um, instantiation from 1. So basically I just said, hey, it's true for this one element. Now, remember that this is an and when we have an and, we can say, therefore, it's true for each one of them. So I'm going to start by just saying dA is true by simplification. Now, you might say, well, why? Why did you choose that? Well, because I know that I'm going to end up talking something about d of x or d of a. And so this just tells me that it's true, and that's going to help me further down the line. So now what am I going to do? I'm just going to give that second premise. Oops, for all x, d of x implies p of x. And that is a premise. And I bet you can guess what we're going to do now, because again, I've got this quantifier. I don't love the quantifiers, so I'm going to say now that d of A implies P of A. So I'm just saying specifically for one element in the domain, and that's universal instantiation or 4. Well, now what? Now I know that if dA is true, then PA is true. And guess what? I already showed up here that DA was true. So that's going to be that PA is true. And that's good old lowest points with 3 and 5. So 3 and 5 with lowest points tells me PA is true. And that makes me happy because look where I'm trying to head up here. I'm trying to get to P of X, or in this case, P of A and not P of A, so I can get to that final conclusion statement. So of course, for 7, I'm going to say not P of A, but I can't just decide not P of A, but I can use it from 2. Remember 2, we said both of those things were true for that element A, and therefore this is just simplification from 2. If we did, I should have put that from 2. Just like we did on step 3 to say that P of A was true. Now I can say P of A is true, not B of A is true, and therefore I'm going to put these together to say P of A and not B of A. And how do I know that? Well, it's me just basically putting together two true statements, which is a conjunction. Conjunction of which one? 6 and 7. And finally, I'm going to say, hey, I just showed that for A, that statement is true. So now I can say there exists some X such that P of X and not P of X is true. And how can I say that? Existential generalization from 8. So hope.
So this is just the general process to do some the proof or inference from this existing logical expression, or all of them called premise. Premise means that have already the just the conditions. Based on these many the conditions, we can just do the inference some the final result. So here example is very popular. That means they have the premise, they have two premise, also have this modifier symbol, and they are just the conclusion also have their modifier symbol. So how to do this proof? And we should be careful. Here we just to combine or just give their special this value A. And we first to use the premise for some existing qualified, and then is the for all or just the universal qualified. If I change this order, that means if you just using the A for the for all, that means for all, and then we just using for some, maybe it is not right, because we know that for all means that it is for every element or every member just satisfy this. But if you just choose arbitrary this special A, but this maybe this special A not satisfy this for some X. So we first choose for some X, and this some X of course to satisfy for all. So for some means that it is a special element. This special element satisfies this. So we just first to choose this special element, and this special element also satisfies for all. But if we just change the order, we are just to select arbitrary element, and this arbitrary element maybe cannot to satisfy this for some element. So we should be careful in the order. So first we just implement instantiation EI or UI refers to EI. Then, based on this special element, we also certify UI. The problem. But if we first UI, then EI, maybe it is something it is wrong, because we know that for arbitrary A, for element for arbitrary A, maybe this A not certified for some X.
And you were able to follow all of those steps. We're clear. I know those can be very difficult. So the best advice is practice, practice, practice.
So here we just already give you some example, and this example just to show you about many about this just inference or proof just using these many of these just the rules. And similarly here is also the similar. It is also the similar videos the example to first to translate this logic expression. And here we have for all logic expression and for some logic expression. And based on this, we want to just to inference the final this result. So we should first to this. We should first this and then choose for some and then combine together. It is similar this example. Okay. And here and this just have already to reduce at the models universal model problems. Okay, this you can easily from the existing book because we know that this it is already to know that for all x px condition qs. So for the particular element A, so we have P A condition Q A. Using the universal instantiation. So based on this, PA condition QA and PA, then we have QA. So it is just using the models problems. We just combine UI and NP together to combine the U and P with new rules. Okay. Just this. This just also can be true because we know that this it is logic equivalence. That means for all x, just not qx condition not px. So just if we have not qx, so not px, it is also easy to extend. Okay, based on this inference, then we can do some the proof for the under the computer or in the computer. So just the first we give some the concept or some the special concept for the related to the proof. First is the theory. It is maybe you have already know many of the theory in the higher mathematics course. Okay. The theory means that it is a statement that can be proved. It can be proved, okay. And axiom means that it is already to basic proof. It is the basic assumption. And there is a lemma. Lemma means that it is just to intermediate result for just the theory. And he is just have these two special, it is corollary and a conjecture. It is just to have the special rules, okay. But we just care about this, how to do our proof. And we have just the first is direct proof. Direct proof, that means if P, we just want to do some the proof. For example, you want to prove from P to prove the Q. We just to do some this the P contingent Q, whether or not it is always true. It is a direct proof. Okay. And from this direct proof, we just also to using to the indirect proof. And this indirect proof just means that because we know that P condition Q is logical equivalence, not Q condition, not P. Okay. So now you just to show that P condition Q is always true. It also means that not P condition, not Q condition, not P is always true. So we want to prove this. It is also to call it indirect proof. And this indirect proof, sometimes we just can be using the contradiction. That means if we say, we just say the result is not true, and from based on this assumption, we want to inference that the condition have some the contradiction, not P, not P. This P means that permanent or just the condition. That means also condition can be after crash. Then we can say it is just say indirect proof, and this indirect proof just sometimes we use the contradiction crash, the crash. And here some the different club and this and we can just show you about some videos. And these videos just also give us many examples.
Is choose odd questions from your textbook and put the answers in the back of the book and just see how you did. Up next, we're going to be taking a look at a lot of different methods of proof. So all of this that we've been doing up to this point is just building a foundation in logic. And now we're going to look at methods of proof. The first of those is direct proof. In this video, we're going to take a look at a method of proof called direct proof. So in a direct proof, essentially we are just going to assume that the antecedent is true and then use the rules of inference, axioms, definitions, etc. to show that the consequence is true. So we're assuming P is true, we're proving Q is true. So that is our goal. We did this a little bit already when we talked about the rules of inference. We did a direct proof, and it was a formal direct proof. So for each and every step, we gave the axiom or rule that we use in order to prove it's true. So on the next couple of examples that we're going to do together, these are going to be direct proofs, but they are going to be informal proofs.
So this direct proof just as a general process to your proof in your many other course. For example, the high mathematics course, it is just to do some the proof. For example, just the homework one, you also just do your proof, show something, something. So for the direct proof, that means just from the existing condition, and based on the condition, you just do your some different rules and to different final result. Okay, direct proof. But the indirect proof, that means we first think of the result, and if just to guess if result is not true, and then try to get some crash with the conditions in indirect proof. Indirect proof, that means we just to think it over from the different the way to do that. The direct proof, that means we just from left to right. And indirect proof, we just to think of this from right to left.
Let's do our first direct proof together. So we are to prove if n is an odd integer, then n squared is odd. Now keep in mind, whenever we're dealing with a direct proof, which is what we're doing, we're essentially looking at our propositional logic. We're saying if P then Q, we're assuming P is true. So it's good to think about that when you're starting a proof like this. In this case, I've got an if then, and so it's pretty clear that this is P and this is Q. And therefore this is an if P then Q, it's an implication. So when I go about proving this, remember I'm going to assume then that P is true. That's a direct proof. Now before I get started on this, I want to talk to you about two definitions that you may or may not be familiar with, but you're going to use them all of the time. When we're dealing with things like even and odd, we need ways to re-express those so that we can manipulate them in proofs or equations. If I'm dealing with an even integer, let's say n is even. If n is even, I can re-express n as 2 times k, where k is some other integer. And of course, the reason I can do that is if you have an even integer, the definition of an even integer is that it can be divided by 2 and the result is another integer with no remainder. If I have an odd integer, say n is odd, n can then be re-expressed as 2k plus 1, because obviously if we take an even integer and we add 1, we get an odd integer. And again, k must be an integer as well. So now that we have everything we need, let's start this proof. When we start a direct proof, we assume P is true. So I'm going to assume N is an odd integer. Based on that, then I'm going to use my definition of an odd integer that says then n equals 2k plus 1, where k is some other integer. And now I'm going to go about proving, and I can say my definition, oops, a little extra something there, my definition of an odd integer. So from there, I'm going to say, where am I trying to get to? I'm trying to say n squared is odd. So if n is 2k plus 1, then I'm going to square each side because I'm trying to get to n squared. So that gives me n squared equals, and then of course I'm going to FOIL this out. So please don't give me 4k squared plus 1 because I can't even. This is 2k plus 1 times 2k plus 1. So FOIL it out. When you do that, I get 4k squared plus 4k plus 1. And that still doesn't help me because what I'm trying to get to is to say that n squared is odd. Now, how am I going to show it's odd? Well, lucky for us, we have a definition of what an odd integer looks like. So I'm going to continue by taking a 2 out of my first two terms, 2k squared plus 2k plus 1. So from here, I'm feeling pretty good because this does seem to be in the correct format. But a lot of people don't like that because there's still kind of a lot going on here. So quite often what you'll see is n squared equals 2r plus 1, where r equals 2k squared plus 2k, and r is an integer. So now what have I done? Now I've said, hey, I've done all of this work. I have found that my n squared gives me an odd integer. So at the end, I'm just going to summarize what I have found. What I have found is therefore n squared is odd. Now, again, those three little dots mean therefore, and a lot of times you'll see then a square at the end of the proof, which is basically saying, hey, I'm done. You might see a little triangle at the end of your proof, or you might see QED. QED is essentially a Latin phrase that says something like what was to be demonstrated. And so essentially we're saying we demonstrated what was to be demonstrated.
So here just to show about the direct flow just from this existing the condition. And personally, the condition just do some many the existing the series, and then we just get the final result. It is the direct flow. Okay. Okay. Now 5 minutes break. Okay, we continue to talk about the directed proof, and we know that, and that means from the logical rules and from the computer side, what they are just understand your proof. That means your proof means that you just want to from P, want to get the result to Q. For example, this example that means here P means that if n is odd integer and q means that uh, n squared is also an odd integer. That means you just do this proof. That means you want to from P to get your result Q. We just use this simple P imply Q. But how to do for the computer world? Computer first to translate this proof direction into just the logic expression. That means he just say P contingent Q is always true. It's just like this. So it's always true. That means we just to from do some the P condition Q just like this. So it is just call if we just from P to condition Q. It is just from it is directed is the proof. And we also let P condition Q is logical equivalence, not Q condition, not P. So it is just give another way for your proof. That means indirect proof. It just give the nature about this indirect proof. Okay. And now we continue maybe another example for the direct proof. Okay.
Another proof for us to try, and it's always a good idea to challenge yourself. So if you'd like, go ahead and press pause and try this one on your own. But remember, when I'm doing something with a direct proof, I'm looking at that if P then Q, and this one isn't really within that format. So if it's helpful to you, not a bad idea to think about what this would look like as an if then. So it says the sum of two even integers is even. So if I add two even integers, then the sum is even. Something to that effect is how I can write this as an if-then statement, which means that I've got two even integers, which is p, and I'm adding them together and getting a sum that's even as q.
So this is just to give some the translate the way. That means if you just to want to using the computer to help us to check or prove this the sentence or this human question. The sum of the two even integers is also even. How to do that? We just translate or change to this like this formula P condition Q because we know that it is can be done for the computer in just their logic rules. So we are just to get if then. So how to change this sentence into the same meaning with if something then blah blah blah. So we just to translate like this.
So for p, I'm basically going to say I have two even integers. So when I get started on my proof, I'm going to say assume a and b are even integers, which is essentially what this is saying. Now, I didn't include the add, but that's okay because over here sum implies that I'm adding. So assume a and b are even integers. Guess what I'm going to do next? I do exactly what I did last time. Then a equals 2k for some k that is an integer, and b equals 2m for some m that is an integer. Now, keep in mind, I have to have different variables for those two. I can't just assume they're the same variable because that would be assuming that a and b are the exact same even integer. So this is allowing for any possibility of two even integers. So that's what I did next. Now from here, I'm going to focus on the math part of it. It says I'm adding the two even integers. So I'm going to say a plus b. I'm saying a plus b is the same as 2k, because that's what a was, and 2m, because that's what b was. Now I can rewrite this as 2k plus m, again using the distributive property. And then I can rewrite that as 2r, where r is equal to k plus m, and r is an integer. That's that z, but you get the idea. So what I said is when I'm adding these two even integers, I get some other even integer. So therefore, the sum of two even integers might be b. I would encourage you to continue practicing the math on your own, but for us to
this just to show you about another example to give this direct proof. Direct proof means that you just give the same from the condition and based on this condition to give to show you the final result. Okay, if it's just not another the way indirect proof. Indirect proof means that you are just to because we know that here P condition Q is not equivalent, not Q condition, not P. So what means not Q? Q is our expected result, but now we are just assume is not Q. And based on this not Q, we maybe cannot find some not P. P is a condition, not P. Not a condition means that it is a contradiction or crash in our the condition statement. Okay, so it is just the indirect proof. So now we just show some the example for this indirect proof.
In this video, we are going to look at the method of proof known as proof by contraposition. Contraposition is a type of indirect proof. So we've just learned about direct proofs. This is an indirect proof that makes use of the fact that we know that if P then Q is equivalent to its correspondent, or it has the same truth value as its contrapositive, which is if not Q, then not P. So in a direct proof, we assumed that P was true and proved that therefore Q is true. In this contraposition proof, we're going to assume not Q, and we're going to prove not P is true. Therefore, by contraposition, proving that if P then Q is also true. Let's take a look at our indirect proof. And again, in our indirect proof of contraposition, we're saying if P then Q is our implication, we're going to show not Q implies not P. So here's P, here's Q. And now I'm going to start by assuming not Q. And if I can show that this relationship is true, it will show that if P then Q is true, which is of course what I'm trying to do. So let's get started. I'm going to assume N is not odd. So I'm assuming not Q. So not odd is the same as even. So I'm going to assume N is even. So N can be represented as 2K because it's even, where K is some integer. By definition of an even integer. From here, I'm going to take a look at the math. So I have 3n plus 2, which is 3, oops, not 2, 3 times 2k, and substitution, plus 2. which is 6k plus 2, which is 2 times some quantity, and that quantity is 3k plus 1. Or just as I did in the last video, I can say 2r, where r is equal to 3k plus 1, and r is an integer. So what have I just shown? I have shown that not q implies not p, because p says 3n plus 2 is odd. And I have just shown here that 3n plus 2 is in fact even by definition of an even number. So I'm going to say, therefore, 3n plus 2 is even, since not q implies not p is true, then if p, then q is true by contraposition. Again, QED, or your box, or your triangle, or however you're ending your proofs. Here's another one for you to try, and I'd really like you to try this one at home because it's exactly the same proof we just did, except I've replaced these with P. So if you would, press pause, try this question on your own. When you're ready, press play to see how you did. So again, I'm still working with this thing, if P then Q. So here's P, here's Q, and in a proof by contraposition, I'm going to assume not Q. So I'm going to assume not Q, show that that implies not P. That's going to tell me if P then Q is also true. So I'm going to assume N is not even, and assume N is odd. If N is odd, then N can be written as 2k plus 1 or some integer k. So if that's the case, then I can take 3n plus 2 and replace n with 2k plus 1. Oops. And then I can rewrite that as 6k. Oops. This is plus 2. So this is now 6k plus 3 plus 2. And keep in mind where we're trying to head, because we're trying to keep things either in this format or in the n equals 2k format. So I'm going to rewrite this as 2 times, and that would be 3k. And then I have a total of 5 here, but notice I've got the 2 here, so I'm going to say plus 2, which gives me 4. And then what I have shown is 3n plus 2 is odd, by definition of an odd number. So since not q implies not p, then if p then q is true by contraposition. Up next, we're going to take a look at the method of proof known as proof by contradiction. And up next, we're going to look.
So here just give the example of using the indirect proof, and this indirect proof just give our ways just to do some proof. That means in let from the condition P, it means let the condition P to give the result Q. And sometimes maybe if you just from P to Q is something difficult to your proof process, then we can just from the another way. That means because we know that the P condition Q is equivalence not Q not P, so it is just the position. This is from the logic rules to give us the way to do now the computation. So maybe in the previous course, just let you to do this computation, but maybe you don't think it over why it is okay. Why we let you to come to prove P condition Q, but you just from a different way, not P, not Q. Why it is okay? It is based on this logical equivalence. So we can just do the conversation. That means sometimes if you find direct proof is difficult, then you can just use indirect proof. That means we first assume the result is not true, not Q, and then whether or not we can just to find the condition is crash. If crash is done, okay. Okay, this is another some the many of these example, and this also example just based on this indirect proof, and we just show you another example about this.
In this video, we are going to look at the indirect proof. So we just look at one more method of proof, which is a proof by cases.
This is another proof, yes. I tested
by exhaustion. I don't have a ton of room for a conclusion, so I'm just going to say that in this video, we're going to take, I'm just going to say the key thing to think through is all of the.
Yes, this is just a by cases, maybe just discussing something.
Which is a proof by cases or proof by exhaustion. When we do a proof by cases, essentially what we're trying to think through is all of the different ways in which a situation could happen. For instance, I'm going to prove if n is an integer, then n is less than or equal to n squared. So here's an implication if p then q. Now, hopefully at this point in your mathematics study, you have determined that negative values sometimes react differently in a function than positive values, and zero often acts differently than anything else. So that is what I chose to use for my cases. I'm going to take a look at what happens when I have a negative value, which I'm saying n is less than or equal to negative 1. So let's think about a number line here for a minute. Negative 2, negative 1, 0, 1, 2. And notice that I'm using just integers. So if I say n is less than or equal to negative 1, that gives me negative 1 and any integer to the left of that for my number line. Case 2 says n is equal to 0, again because 0 often reacts differently than other things. That takes care of 0. And n is greater than or equal to 1, starts at 1, and gives me anything to the right of that. And so you might be thinking, well, that's great, but look, you've got some spaces here, so you're being sloppy. Now, if this were any real number, not any integer, then those spaces would be a real problem. But because I'm dealing with integers only, then this is an exhaustive proof because I'm using all of the integers less than or equal to negative 1. The next integer is 0, which I've covered. The next integer is 1, and then I have everything greater than 1. And so this isn't going to be now, if I'm comfortable with those spaces, instead just say n is less than 0 and n is greater than 0, and you're going to get the same result.
So here just to show you about if you just do some also is direct proof, but sometimes maybe their domain is special. So for the special domain, if you want to just divide this domain into many parts, but you should be careful. These parts should be combined or cover all the possible cases. That means all your just the cases. If you just combine all the cases, should be is just search or just to make the need or just cover all the possible cases, okay?
Now that we know our three cases, let's go about making this proof happen. Case one says n is less than or equal to negative. Keep in mind, what I'm looking for each time is to show that this relationship is true, that n is less than or equal to n squared. So what happens if I have a negative value? If I have a negative value and I square it, n squared is always going to be positive. It's always going to be positive because a negative times a negative is a positive. So therefore, it follows, n is less than or equal to n squared because n squared is positive and n is clearly negative. Now, notice I didn't write all of those words. I would write all of those words if I were doing this for an assignment or a test. Case 2 says n equals 0. Whenever you have an equal, you just do direct substitution. 0 is less than or equal to 0 squared, and 0 squared is of course 0. 0 is in fact less than or equal to 0, therefore it follows that n is less than or equal to n squared for case 2. For case 3, n is greater than or equal to 1. So if n is greater than or equal to 1, and I multiply the left side by n, and I multiply the right side by n, I end up with n squared is greater than or equal to n. So it follows that n is less than or equal to n squared. So how would I wrap this up? Since n is less than or equal to n squared for all cases, or for all values in our domain, we can conclude if n is an integer, then n is less than or equal to n squared. Let's take a look at another proof. This is a proof of an implication. If P, then Q. And again, even though there's no then, that's okay. And what I'm looking at now is how do I prove this? Well, in our last proof by cases, we were concerned about the sign of the value, whether I'm plugging in a positive, a negative, or a zero. Here, instead, I'm worried about the period, whether something is even or odd. So I'm going to have three cases here. I'm going to say case 1 is n is even. Case 2, n is 0. And again, I'm using 0 because 0 is not considered even or odd. And then case 3 is n is odd. Because based on what I'm trying to prove, that something is even, I know that what I plug into it may have some effect on the outcome. So if I start with case 1, I'm saying n is even. So therefore, n is equal to 2k for some k that isn't an integer. So then I'm going to take n squared plus 3n plus 2 and just continue to do the math here. So if I square this, I get 4k squared plus 6k plus 2. And then if I take a 2 out of everything, I get 2k squared plus 3k plus 1. And remember the way that we did this before is quite often we'd say, well, that's equal to 2r, where r is equal to all of that stuff. 2k squared plus 3k plus 1. So why does that matter? Because what I've just shown is that for case 1, if n is an integer, then 2n, or sorry, n squared plus 3n plus 2 is even. So 1 out of 3. Case 2, again, this is just an equal, so I'm just going to plug it in. 0 squared plus 3 times 0 plus 2 equal to 0 plus 0 plus 2, which is equal to 2, and 2. Last I checked, even. Case 3, n is odd. So if n is odd, then I'm going to say n is equal to 2m plus 1 for some m that is an integer. And I'm going to do the same thing I did before for case 1. And I'm going to say n squared, so n is now 2m plus 1 squared, plus 3 times 2m plus 1 plus 2. Remember that I'm foiling this, I'm not just squaring each of the terms. So that gives me 4m squared plus 4m plus 1. And then I'm distributing the 3, so that's 6m plus 3, and I still have the plus 2. And then I'm simplifying to get 4m squared plus 10m plus 6. And then I can take a 2 out of everything to get 2m squared plus 5m plus 3. And again, I can say all of this stuff is equal to, say, L, where L is equal to everything I had in there, 2m squared plus 5m plus 3, which is even. And again, then I just summarize. Therefore, n squared plus 3n plus 2 is even if n is an integer. Or, of course, you could say if n is an integer, then n squared plus 3n plus 2 is even. You get the idea? It's the same thing.
So here we just should to make some complement. That means for make some also the note for this example. That means for some the view. That means sometimes we just make this zero, this number zero, just belong to the even. Sometimes they say it is because also it's 35 equal to times k, and this k is equal to 0. So we can say uh, 0 also belong to the case 1. So if from this view, that means we just only the two cases. The case 1 is even and the case 2 is odd. Okay. We tend to care about this 0 because 0 is belong to even case. So from this view, we just using the two. But sometimes maybe in the previous view, they just say there is a special cases or special number is not belong to even, also either belong to even, not belong to odd. So it is a special. But now we also to accept that there is even. So if you just using the two cases is also okay.
Or, of course, you could say if n is an integer, then n squared plus 3n plus 2 is even. You get the idea? It's the same thing. I'm going to go through just one more proof with you, but this one's kind of a doozy, so I'm going to spend quite a bit of time on it. The reason this one's a little bit different is it still is an implication, which we're used to, but if you'll notice, I quite a bit going on here in the first part of my implication, and then my second part, this is both x and y are equal. So I want to talk to you about how this would look using propositional logic. If I let P represent x times y is even, and if I let Q represent x plus y is even, and then I let R represent both x and y are even. This is the way I'm choosing to do it now. As we know, there's lots of different ways to represent things using propositional logic correctly. This is the way that I'm going to do it. So based on the way that I have assigned my propositions, I can rewrite this statement as if P and Q, then R. If x times y is even and x plus y is even, then both x and y are even. And again, I totally skipped this our integers part, but again, I would just say for the domain of integers. Now, the reason that I wrote this using propositional logic is because though I'm going to use a proof by cases, I'm going to also use a proof by contraposition. So if you'll recall, a proof by contraposition says if I'm showing if P then Q, a proof by contraposition would assume not Q, and you would then prove not P. The reason I bring this up is because if I do that here, then I'm saying if not R, then not P and Q. And hopefully we can do Morgan's law that says not P and Q would be not P or not Q. So what I'm going to do is I'm going to assume not R and then show that either not P or not Q is true. Now, one more thing that's going to make this a little bit more complicated, because obviously this is a proof by cases. Let's think about what my cases are. So I could have that x is odd and y is odd, or x is odd and y is even, or x is even and y is odd, or x is even and y is even. So you might say, okay, cool, we've got 4 cases, let's get started. But that's not quite the case. I'm assuming not R. R says both x and y are even, so I'm assuming that's not the case. I'm going to assume case 4 is not a possibility. So that leaves me 3 cases. And that's just fine. But I want to introduce to you a concept of what's called without loss of generality, because you're going to see this throughout your studies, and I don't have a full video on without loss of generality. So essentially what this means is if you would take a closer look at case 2 and case 3, and I'm looking at what's going to happen with P and Q. Case 2 says x is odd, so let's just make up an odd number. And let's say I'm multiplying that by an even, because again, I'm looking at case 2. So if I multiplied these two, I would get an even number, and if I added these two, I would get an odd number. Now let's take a look at case 3. X is even, y is odd. So let's say I take 2 times 3, and I get an even, and again 2 plus 3, and I get an odd. So what I'm telling you is based on what case 2 and case 3 are, and based on the propositions that they are affecting, case 2 and case 3 are exactly the same. So when we use something called without loss of generality, we're saying, I'm going to assume something is true and it's not going to affect the outcome because there's, for instance, more than one case that has the same outcome. So without loss of generality, I will assume, I'm going to use that arrow to indicate it's an implication. Without loss of generality, I will assume that x is odd. Again, why? Because I'm just going to show case 1 and case 2, and I'm not going to show case 3 because case 3 is going to give me whatever happens with case 2. So now that we've done all of the setup, let's actually do this proof. So I've made the assumption without loss of generality that x is odd. Therefore, x could be written as 2m plus 1 for some m that is an integer. My 2 cases are that y is odd or that y is even. Now, if you recall, what I'm trying to show, so before I actually get started on it, I'm trying to show either not this or not this. Again, by De Morgan's law, which we went through just a few moments ago. So let's see what happens. Case 1, I'm going to find x times y, and I'm going to find x plus y, and I'm going to see what happens. And remember, we're saying these are even, so if I'm saying not that, I'm really just looking for one of those to be odd. So I'm looking for one of these guys to be odd. So x times y would be 2m plus 1 times, we're letting y be 2n plus 1 because it's also odd. And if I FOIL, I get 4mn plus 2m plus 2n plus 1. If I take a 2 out of the first three terms, I get 2mn plus n plus n plus 1. And again, I could just rewrite that as 2r plus 1, where r represents 2mn plus n is n. And therefore, this is odd because it is written in the format of an odd number. I'll move over this x plus y because obviously I want to run out of room if I don't. So x plus y, and I could stop right there for case one because I've already shown that one of them is odd. But let's go ahead and just see what happens. 2m plus 1 plus 2n plus 1 gives me 2m plus 2n plus 2, which gives me 2 times m plus n plus 1. 2 times something, this is an even. But again, I'm not concerned by that because I just need one or the other to be odd. So far so good. Case 2, again, I'm still looking at x times y and x plus y, but now y is even, so y is represented by 2n. So x times y would be 2m plus 1 times 2n, which gives me 4mn plus 2n. This clearly is going to give me an even value. But again, I'm not concerned unless this guy is also even. So now let's try this guy and see what happens. X plus y would be 2m plus 1 plus 2n. I could rewrite that as 2 times the quantity of m plus n plus 1. And again, I could rewrite that in another way, but this is clearly an odd number. I don't have a ton of room for the conclusion, so I'm just going to say the conclusion aloud that if x and y are integers and both x times y and x plus y are even, then both x and y are even. And again, this was a proof by contradiction and contraposition.
So just for this example, that means if not using the contradiction, and we don't use some this indirect proof, maybe it is something is boring to or very difficult to do your proof, direct proof. That means if it just from this to the condition, because this condition is x times y and x plus y are even, and that will show both x and y are even. So it is difficult for you to think it over just from the direct proof. But if not, if it just indirect proof, just like this. But if we didn't use in the already the logic equivalence rule, indirect proof and something is also boring. Both x and y are even is not true. What is meaning? And how to get the crash for both x times y and x plus y are even. So it also made it boring. Just use the composition. That means now don't worry, we're just using some this the Morgan law, the logic equivalent. So that is why our course just give you some the simple way, just using the logical rule to make sure make the exactly the understanding of this composition. Otherwise, maybe you're just thinking over just buy and buy using the natural language, but sometimes maybe you are not sure whether or not it's true or false. You should make to kill and just to check and check. But if you just use logical rule, that means it is okay. Because this the R is this, so both X and Y are even. So not R, not R, just like this here. Not I have many like cases. And here is the crash the condition. Crash the condition P and Q. So not P and Q, it just means not P or not Q. So finally, we are just to show not P and or not Q is okay, just as this done just to do this, just to find it is here is all, here is all. One of them is odd is okay. So if you just find one of them is odd is okay. Otherwise, if you don't understand you both all of them is odd, that is wrong. It's logical. So if you just have a logical example or logical expression, and based on the logical expression, is just to give out the best way or quick way to do out the general the proof. Especially not only this proof is not out the mathematics or computer, maybe in the physics or any other course, just using this logical expression, just also this difference the ways just to give out this way. So it is just some example to give us the injection or direct proof or indirect proof, or sometimes this the inject proof, sometimes or it is uh, contradiction. Okay, so just means contradiction proof. Okay. Now we just have oh, it is for the discussing time. Now discussing time. Any question you can discuss in here. Any question?
No, shouldn't be.
Okay, bye bye.
There's no problem.
Yeah, if no question, that's all today. Bye bye.
再见，陆续。
再见。Okay. Bye bye.